some the topic of sequence and its convergence. So we will first start our discussion with the definition of a sequence. So what exactly is a sequence? Sequence is just a function. Okay, let me explain. So it's there are two sets. So this set is called domain. Domain is A, and this set is called codomain. So a sequence is now in the case of sequence, there the domain is actually the natural number set, and the codomain, when we are talking of real sequences, the codomain is real number set. So what happens to natural number set consists of 1, 2, 3, 4 and up, and this is a real number. So what we do is assign a real number to each of those natural numbers. So these are respective natural numbers. Yes, they may coincide. Yep, they may coincide. And so we all know that this is just another representation of a function. So it's like we are assigning number to 1 as of f of 1. So many times we write like this: f of 2 as a2, and so in an is equal to f of n. So this is to see what exactly is coming down to. That sequence is a function from the natural number set. It's a function from the natural number set to the real number set, and that's called the real sequence. Okay. So now we will do some examples of sequences, the real sequence obviously. So it's easy. Okay, so take like an equal to 1 by n. I mean fn equal to an equal to 1 by n is one such example. Another, there are hundreds of examples. You take any function and that will be and that will be a quite good example of sequence. So if take n equal to anything, e to the power n minus cos of nx, so anything, there are lots of functions. So now we will get to learn how to draw sequences on an xy plane. So take the sequence f of n equal to 1 by n. It's a very easy example. So you may have done hyperbola and all the conic sections, so you must have known how to draw this function 1 by x. If you don't, then it's not too tough though. So the graph of this function looks like this. Okay, so this is 1 by x, I mean y equal to 1 by x, and this is x. Now what we do, we just take the values of the integer points with the natural number points. So 1, 2, 3, 4 and all this. So you take this point and corresponding to this point, corresponding to this point, and we go on, and we wrap the other real number parts. So now we will do this. So we first draw the function and then rub off the other parts. We take the values of the natural number points. So these are the only points of the sequence to draw on a xy. So one thing is important, that see the structure of the actual function actually gives an idea of how the sequence behaves. But we will later on see that the structure of the sequence doesn't always determine the structure of the function. Yes, it determines a part of the structure of the function, but not always. So we will see it in the later lectures. Now we will learn how the concept of convergence. So what exactly is convergence? Convergence is exactly the behavior of the sequence. This sequence of fn equal to 1 by n. So any sequence when n gets larger, I mean when n tends to infinity, goes to infinity, how the function behaves. I mean whether the function takes multiple values, whether function converges to some values. For example, in fn equal to 1 by n, see the function 1 by n actually gets come closer to 0 as n gets larger. So it reflects that the convergence is the property of the numbers of the sequence at infinity, I mean at larger sets, so larger numbers. So now, and this implies that if we change finitely many numbers randomly at any point, finitely many, suppose 10,000 numbers in the sequence, so sequence is infinite set, right? So then it will not affect its behavior infinity, because because it doesn't hamper the numbers at infinity. There is a mark after which it doesn't hamper. So that's the thing, and we will see that that's actually the case when we mathematically study the concept of convergence. So convergence actually contains a lower amount of information than actually what the sequence does. So now we will take this sequence 1 by n because it's the most easiest sequence to see the convergence fact, because it gets closer to 0. It's intuition, right? N gets larger and it becomes less and less, but it is always remaining positive. So the graph is always above the x-axis, but it is getting closer to 0. Now we will study the convergence by studying the property of this 1 by n and how the idea of mathematical form of convergence came into play. See, so we want to establish the fact that as n tends to n big gets larger, to I represent n tends to infinity, the fn goes to 0, I mean gets closer and closer to 0. So how do I define this fact mathematically? So if you observe this sequence very closely, right, that okay, so it means that okay, so take any length, any positive number, say 1, around which you think that it is tending to, for example here it is tending to 0, so take a length of 1 which is tending to 0. So drawn the sequence f of 1 by n here. So now we will study how it gets closer to the y equal to 0 line. I mean how the function the sequence gets closer to 0 as n grows larger. So see, take a line, take any interval around the line you want. See here it's y equal to 0 line, it's getting closer to, so take any interval around the y equal to 0 line, and okay, so let's first take the interval of 1. So here's the interval of 1. Now see that this is the line 1 to minus 1. In the limit it's L plus 1 to L minus 1. Here L equal to 0. If you are assuming this L minus 1. So see that in this interval, from the starting itself, all the sequences are lying in this range. 1 half, 1/3, and it's going all less than equal to this 1. So okay, let's try to take another smaller interval, strip of line. Okay, so let's take 1/3. So L plus 1/3 to L minus 1/3. So see, first few numbers are not in the strip, but after certain time all the numbers are within the strip. And if you take a smaller and smaller interval, the number after which all the numbers will be inside that strip will be getting larger, but still there will be a number after which it will be inside, all the numbers after that number will be inside the strip. So that's exactly the point of convergence we will try to establish. So what we are doing, we are thinking about the limit L, a positive number greater than 0, and which we fix previously in our mind, and then we take an interval this, I mean the strip of line, and see after which number n, after which number n, all the numbers n greater than or equal to n, a of n will be inside this interval. And this is exactly the same thing we will formalize and write in the mathematical definition of convergence. So I am drawing this picture. Now before doing this, I want to introduce one important concept of, I mean, this for positive integer. This concept has is being motivated by this fact. See, this is a very beautiful and simple example. So how do we define a equal to b in some other sense? So take the number x is equal to a minus b, and see a equal to b, and take its modulus. Now we can easily prove that a equal to b if and only if modulus of a minus b is less than epsilon for all epsilon greater than 0. And this part, if a equal to b, it follows, it's very trivial, right? Put a equal to b 0, 0 is less than any positive number. Now we need to do the other, right? If a is not equal to b, so it must be some positive integer greater than c, and see that we can prove a contradiction that c is greater than epsilon for all epsilon less than c. So it's another way of, I mean, there is a dynamic way of controlling. I mean, we take all the positive numbers greater than 0 and seeing whether it's an algorithm type of thing. I mean, there is a dynamic way of numbers are coming, and we are seeing that the sequence is less than every number. So it's about a moving thing. We are taking the numbers one by one of positive numbers of our choice and seeing whether it holds. So it's actually an important concept, and this is used many times in computers, because the computers, we cannot compute everything right like this, a equal to b, so we do like take an error. So this is the error thing. So not exactly this concept, but these concepts of for all positive integers. So this is an important thing, and this type of thing will be applied in this. So this is an easy concept to grasp. So I am just introducing this so that we can learn it here. I mean, we can understand it here easily. Now definition of convergence. This is important. So see, we take all positive integers. So for all, I hope you know this symbol. It's for all epsilon positive number greater than 0. I mean, in your mind, fix an epsilon and do it for all positive numbers. That's the thing it's telling. There exists a natural number n, and you will, as we have seen that as epsilon gets smaller and smaller, we take a smaller strip, the n after which all numbers lie in that strip is getting larger and larger. So not every time it will get larger and larger, but it's dependent on epsilon. So we vary the epsilon, the n changes, and you can see it in a if you think it in your mind. So it's a function of epsilon, and such that this is sign for such that for all n greater than or equal to n of epsilon, the distance between this n is lying between this, it means that n minus l is belonging to this minus a to l. So it means modulus of a n minus l is less than a, right? This is the thing. So I mean, if this is lying between a and l, means is less than a and greater than minus l. So take the modulus, it will give this thing. So it's the same thing. So the distance between that, I mean, this means that the distance is getting smaller and smaller, is less than epsilon. So this is the whole thing. This is very important, convergence definition, and it's intuitive, it's motivating, but not at the first sight. So we need to really explain that part, that why it is. See, there is a one striking similarity between the definition I have given, that A equal to B if and only if modulus of A is less than epsilon for all epsilon greater than 0. There is striking similarity. So and there is one extra information, this thing, right? This actually, without this thing, it's exactly an equal to L, and this actually, it means that it is a property at infinity. I mean, as n varies, so, and you will see that n gets larger and larger. That's actually, if it doesn't happen, then it doesn't converge. So, and one thing I forgot to mention, that L is the limit. We are assuming it, limit of the sequence. I mean, which we think. I mean, this is one of the main drawback of these definitions. So there is another different definition for convergence in this type of distance form. So that's Cauchy sequence criteria. So that is a better thing because there is no concept of limit. But see, that's to prove that a sequence converge, we need to know the limit, or we need to think of the limit. So there are many cases we cannot think. So what we do in that case? So we will all learn this in this future lectures. And see, we need to know this limit. This is the most important point of definition and the most drawback point of this definition. And another thing which I was telling, that here this extra information is given, and this means that n grows larger and larger for different epsilon, and this means that it's a property of the infinity, at infinity, and it's a dynamic property. This is moving for every epsilon, not constant. And if we remove this, I mean, it holds for all n, then it obviously implies that n equal to, I mean, for all n it's equal to L. So same thing. That's also convergence, right? So it's an important information, and it's actually provides a much more insight that the convergence is a more lower dimensional property it's occurring. Here, once in the previous slide, I have told that as epsilon gets smaller, in infinity changes, right? I had mistakenly told that it goes to infinity, but it's not true. I mean, if the sequence generally freezes to the limit after some point, like this. So take this sequence, right? Okay, so 1/2, 1/3, 1/4, we are taking this, and after 1/10 we take all them to 0. See it after freezes. So after 10 you will see that the n of epsilon is always 10, so the minimum n. So actually n doesn't freeze, and we can even show that if n doesn't freeze, I mean, if n continues to grow as epsilon in epsilon goes to infinity, as epsilon tends to 0, it happens even only if it is not subsequently equal to 0. I mean, the limit, I mean, it varies in some sense. So this is one important thing I forgot to mention. So that's it. And these are much more theoretical part, right? So we for basic understanding, yeah, it's important, but we need to see now how this is applicable to the normal functions, the function sequence. So I will now prove how it is applicable to the sequence that we are doing 1/n, and just clarify our intuition. And so first I will do for the sequence 1/n, and for the 1/n square I will provide a slide of picture that contains the proof, so we can understand. And now we will get to know something important, interesting, and the drawback of this, and so we want to concentrate on other facts, how to move on from this. So take the sequence 1/n and take epsilon, any epsilon. So take it 0.1 here. So one side I am doing 0.1 and one side I am doing epsilon. So we want to get some n of epsilon such that it holds. So given we take an epsilon of our choice and then we find an n with respect to the epsilon such that this holds for all n. So we need to find this. This is the most important step given this. So we assume that the limit is 0. This is the most important step and the most unintuitive steps in case of much complicated functions. So n minus 0 is less than epsilon, and here n minus 0 is less than 0.1. So here it's coming n modulus is less than epsilon. So and we put the value of n, right? N is positive, so we remove the modulus sign. So it's coming, and similarly it will come here 1 by n is less than 0.1 and n is less than greater than 10. So this property holds when n is greater than 10, and this property holds when n is greater than 1 by epsilon. So this is a general formula, right? So I just have given it here to see what is happening for an arbitrary epsilon. So as you see, one thing, you take epsilon equal to 0.001 and n is coming out to be greater than, it holds if and only 1 by 1000, and see it's increasing, right? So it's not always the case that I was telling, but and because it's non-homogeneous, I mean you're not freezing to the limit after some time. So n is 1 by epsilon, so not always n will be of this fractional form so that it becomes integer. So we now need to tell that n of epsilon, we just, our method is now, algorithm is now to take the number just next after this number. So we take this number to be the integer part plus 1, just the next number after this number, and if it's and it doesn't actually very much. So this is the thing. So yeah, this at first when you see this thing, it's very ridiculous, right? Where did this come from? Where the hell did this come from? But after doing this step, it's clear, right? So this step is important, not this, but this step is very important. So remember this. So we get that n f epsilon, that is 1 by, and the limit is L here, so it's very trivial, right? I mean, yep. So that is the proof, and once you see the proof of 1 by n square, you will also get to know how 1 by n comes to the proof. So this is the main idea actually, and it's very easy in this case, but not always. So we need to think something different, and that's what we are going to do next. I have told previously that we have the function we are going to do is 1 by n square. It's not, it's 1 by root n. So we provide in the slide. You please pause the video and see it. Okay. So now one another thing that now we are trying to concentrate on how the epsilon, I mean you have seen one thing, right, that epsilon is I mean n of epsilon is dependent on n. So I am going to take this arbitrary function, it's very bad, right, e to the power minus 1 by n into sin nx by cos nx. Then you will see that epsilon, we have to find that epsilon by what we are doing, like we are doing it by like this and all those things, minus L. So it's a complicated equation, very complicated equation. It's very hard to find. Even if we are taking to be a polynomial equation, it's hard to find the roots. So this method of finding n of epsilon is very bad, and it can't be actually many times by normal methods. But we can say that about how the n of epsilon behaves when epsilon goes to 0 and becomes smaller, as I have told. But now what we are going to do is, we have done some basic facts, right? The basic facts are how 1 by n limit goes to 0, 1 by n square we will see limit goes to 0, now 1 by n to the p we will see the limit goes to 0. So I will provide a slide, another slide setting some basic limit results, and it's easy, right? You will get to know. And another thing, in the slides I will first provide all the information, right? The various theorems and the results, and then I will provide the proof. And we will see that we can also provide the proof in the comments in the description section also, or we can also provide the proof in the video section where you can pause and see it. So we will decide, you will see in the video. Now we want to use these well-known sequences 1 by n and 1 by n square, and this whose limit are known to 0. How can we use it? So we take a function. We will provide some properties of the limits, how limits behave when we take we do an operation of limits, like we add and divide. And the important properties are this. First of all, it's intuitive, right? The limit of a sequence is unique. Okay, so we all state its properties and the theorems and results, and we will prove it. I mean, we will not prove it on the board, but we will give the proof as the description, a link or a picture or in the video. Please see it, because it's very important if you want to go into the theoretical parts, or if you want to just practice or know the basic all. I mean, the video is so arranged that it's all compact in here, so it will help you, I think. So it's the limit is unique. This is a thing. Thing is, every convergence sequence is bounded. Okay, let me explain this in some simple languages, then you can understand the proof, I think. So suppose a sequence has two limits, okay, this L1 and L2. Now what we know about the limits, it's beautiful, right? After certain epsilon, all the numbers, they exist in n. So take an epsilon such that these two strips of line are disjoint, both around. So it's L1, it's an epsilon distance around epsilon, 2 epsilon distance around L1, and it's a 2 epsilon distance around L2, such that these two strips of line are disjoint. Now for this epsilon, there exists an n1 for this L1, such that after all this number, all the numbers in sequence lies in this. Again, there exists an n2 for this L2, after which all the sequences lies in this sequence numbers. So it means after maximum of these two numbers, say n2, all the sequence also lies in this. So it's a contradiction, right? After n2, all the sequence lies in both this and both that. So and both are disjoint. So it cannot happen. A sequence has a unique limit, and it's beautiful, right? It's actually intuitive and it's beautiful. And this is the same thing put into mathematical form in those epsilon and these modulus things, and it's the same thing. You get to understand. And now we count every convergence sequence is bounded. It's also easy. Take a convergence sequence. So is it a limit? So take an epsilon, any epsilon. Suppose you take any epsilon, or you take 1. Okay, so it's L plus 1 and L minus 1. And for this, see, they must exist an n1, such that after all the n1, all the sequences lies in this strip. So after n1, all the sequences are after n1. All the sequences distance is less than, I mean distance from the, and it implies n is less than L plus 1 and greater than L minus 1. So this sequence after n1 is bounded, right? And the definition of boundedness of a sequence is given in the slides, so please refer to it. So it's bounded, and see, this for this one, this is a finite number of numbers, finite number of n's here. So in this one, a1, a2 up to a of n2, take the maximum one and the minimum one, and in this you also know the maximum and the minimum, the bound. So the an is bounded between maximum of a1, a2 up to an2, comma l1 plus 1, and greater than equal to minimum of a1, a2 up to an 1 comma L minus 1, and see, it's bounded and it's easy, right? All this, you draw the picture and you will get everything. This geometrical fact is very necessary for getting used to mathematics and its understanding, according to me. Now, okay, I am sorry I rubbed it. So another two things are algebra of limits, and another thing is order of limits. With order of limits, you will see you take a sequence, multiply any constant, suppose the sequence goes to A, multiply a constant with each of every term of the sequence A, and it converges to C of A. It's simple, right? It can be seen when you draw the graph. It's beautiful, right? Just magnifying the images, and so the limit also gets up. All the things are getting up. So it's just same. Now for the order of the limits, it's just described that if two sequence behave in some inequality, I mean An is greater than or equal to Bn, how the respective limits will behave. So first thing is this, and all these proofs are very easy. You can find it in the description or the video afterwards. And so the limit, if it goes to A, the limit also is greater than or equal to A, and it's very easy, right? If all the sequences are greater than 0, so the limiting point will also greater than 0. And another example is 1 by n. The limit is greater than or equal to 0. So equality really holds actually. So when I mean n equal to 1 by n, all are greater than 0, but the limit is 0. So equality may hold if all are strictly positive. So this is an important point. And next thing is just a consequence of corollary of this. It's if A is greater than or equal to Bn, then limit n is greater than or equal to limit Bn. Just for this proof, just tool An equal to An minus Bn, consider it to be Cn. So from here Cn is greater than or equal to 0, so limit Cn is also greater than or equal to 0. So from the algebra, limit Cn is equal to this algebra of the limits, so is greater than or equal to 0, and there is a result. This is simple corollary. And the third thing is, if I mean boundedness, right? I mean it's just a thing. I mean this is Squeeze Theorem, and it is given as a exercise. You can freely comment the answer in the comment section. And it says that if An is less than or equal to Bn and greater than or equal to Cn, and it both goes to the same limit L, then it is sandwiched and squeezed to go to L. So that's the thing. It's a beautiful property, and you can use it. And why these are important? Because you see, using this all this algebra and thing, we can prove that 3 plus 1 by n by 4 minus 1 by n goes to 0, and it's beautiful, right? Here it is 0 and it's 0. Now we will show some geometrical properties why Squeeze theorem is really applicable. It's beautiful. Take this limit. So we know that two sequences converges to this limit. So any sequences in between them also must converge to it. So I draw the sequence of the function because it's continuous and it's easy to draw. So take this thing, and another thing is like this. So what happens if anything lies in between two? It is bound to go to the same thing. I mean, it's very bad graph here. So consider another graph, say like this and like this. So for this example, okay, I will give an example though. This is the y-axis, this is the x-axis, and see, if any function lies, any sequence lies in between this, so it will go to the same limit. For example, this thing. So it is going in between them, but still is going. So this is exactly the same. I mean, it is forcing, the inequality is forcing to go to the same limit. And when you prove that thing, and show it in the comment. You will get to see why it is. It's beautiful. And feel free to comment and write any answer. It may be wrong, but you're trying. That's it.